All right, so let's talk about another intermolecular interaction called London forces or London dispersion forces. London is the last name of somebody. I'm pretty sure. It might actually be after a conference where they kind of identified these structures. I can't remember the history behind that. Somebody could look it up for me. That'd be good. I'll give you extra credit. But dispersion forces is a much preferred name because dispersion forces, you don't have to remember what London means, right? Dispersion forces occur on compounds where there's no dipole, but there's this always, because of the motion of electron density around compounds, there's always what we call an instantaneous or induced dipoles, all right? So here I have a chain of 1, 2, 3, 4, 5, 6, 7, 8 carbons, all right? 8 carbons. I'm not showing the hydrogens. I'm just showing clouds around them in these purple circles here as electron density. And we can imagine these nuclei having electrons kind of moving around. And as those electrons move around, there is some motion of the electron density. The electron density kind of bounces around and moves. Now, if we were to look at any one instantaneous moment by stopping the motion here and seeing, oh look, for this moment that I stopped it, the electron density on these two or in this region of the compound is kind of moving off of the compound, off to the right here. And it's exposing a little bit of this nucleus maybe. And so you could think of, at this really, really small moment, here's a partial positive charge here and a partial negative charge there. Do you see that?
Yeah, I can see that. So you're saying that the electron density moves off to the side and results in a partial negative charge, leaving behind a partial positive charge on the nucleus that it moved away from?
Yeah, very good. And we call this an induced dipole or an instantaneous dipole because it's not, doesn't last very long, right? And but these London dispersion forces can be influential if the ability for the electron density to move is large. So, for example, if you have a very large atom, you can think of that electron density around that atom as having the ability to kind of sway back and forth. And when it sways, I know it's swaying really fast, but when it does sway, it creates an instantaneous, momentary dipole. All right? So, if we think about two molecules here, two molecules, and their electron density is just kind of moving around. And if I say, okay, stop and find out, there it is, I stopped it. And I'm looking for a little bit of places where there's a partial, what would the partial charge be here? See, the electrons have moved. What would be the partial charge on this section right here?
You mean around the nucleus?
Yeah, right here. Right here, what would it be?
That would be partial positive, right?
That's right. And where would the partial negative be?
Oh, down there, where at the bottom of the sphere.
Right here. Yeah. Good. So, that is an instantaneous dipole. And look, up above here, you have a similarly instantaneous dipole where the electron density is partial negative here. And so what that does is it would result in these two molecules sticking together because of this instantaneous dipole or induced dipole, right? Two dipoles that were just instantaneous, just short amount of time, but they cause the two molecules to stick together. That also might occur here where we have a little bit of positive charge and this negative charge is reaching out even to this one here, okay? This area right here has, I mean, it's not really swaying off of the nuclei very much, and neither is this area. So these two regions wouldn't attract each other. But these two, right now, the way I froze it, would attract each other. So if I do the slot machine again and stop, ooh, got the same thing basically. Let's try again. Okay, so this time I did it, and these regions of overlap are going to repel each other, right? Here's a little bit of positive charge, and this might be able to reach it. If it was able to reach it, there would be some interaction between the molecules, but the interaction is no longer here or over here. It maybe be a little bit over here. But so as this molecule moves, it's kind of like a slot machine because there's just a chance that the intermolecular interactions are strong enough to keep them together. Now we can increase this chance by making a longer chain, right? Because if you have a longer chain, then you have just increased likelihood of spots occurring where partial positives on one molecule and partial negatives on the other interact, okay? If it's a small system, small molecule, how do you think that influences it?
It's going to be hard, right?
That's right. Whoops. Whoops. I thought I could stop this. Oh, it's not stopping. But yes, it's going to be hard because there's just fewer atoms. So the likelihood of there being instantaneous dipoles at the same place at the same time is slim, right? Let's do this again just because it's just so darn fun. Stop. This time we have partial positive charge here, but this partial positive charge is there also. So not a lot of interaction here, but here, partial negative, partial positive, partial negative, partial positive. So the stickiness wasn't over here this time, it was over here. Here's some repulsion occurring, right? But the idea is, as the longer the molecule is, there's a chance that, an increased chance, that intermolecular interactions will change this from either a gas to a liquid or from a liquid to a solid. Okay. You also get something, a property or a phenomena which is called electron synchronization, where because one moves and the other one is very close to it, it begins to kind of follow the motion of the other. And when that happens, then you can get even augmented, even an extra amount of interaction between molecules. Okay, so look at this. See this compound, CH4, one carbon, has a melting point of negative 183 degrees Celsius. That means at 183 degrees Celsius, or let's look at the boiling point. At negative 162 degrees Celsius, it changes from a liquid to a gas. All right? So it's got to be really, really cold, colder than negative 162, to make methane turn into a liquid. All right? However, that's one carbon. If you put 7 carbons together and make heptane, then the result is a boiling point of 98 degrees Celsius. So at room temperature, heptane won't boil. You have to heat it up to 98 degrees Celsius to make it boil. And you can see how the change in even C18 and C20, these are solids at room temperature, right? And so what we're seeing here is that because the longer chains, then there's an increased likelihood of these dispersion forces occurring and a change in the physical properties, melting and boiling point, and its state, gas, liquid, or solid, for these compounds. There is also a dependence on the shape of the molecule, and that's because molecules that are kind of globular, like this one, are going to have a decreased likelihood of a neighboring molecule being able to induce a dipole because it just has a smaller surface area where the interaction can occur. A longer chain, so this is the same compound in terms of its chemical formula, C5H12, C5H12 for both of these, but the boiling point here is significantly higher than the boiling point here simply because the shape of the compound. All right, so we've talked about intermolecular attractions. We've talked about dipole-dipole interactions. We've talked about hydrogen bonding. Hydrogen bonding is an augmented dipole-dipole. And we've talked about London forces. London forces. Nonpolar covalent compounds, they really only have London forces going for them and a little bit of this electron synchronization, but dispersion forces is about all they have. Another name for dispersion and London forces is van der Waals interaction, named after a different professor who worked on studied these phenomena. So van der Waals interactions, London forces, polar covalent compounds that don't contain a hydrogen, then they can have dipole-dipole attractions and London forces. We don't want to forget that just because there are dipole-dipole interactions, it doesn't mean that London forces don't exist. And you'll see changes in physical properties, boiling point, melting point, its state at a given temperature, right? Simply by from a contribution of London forces or dispersion forces. If you have a hydrogen bound to one of the big three electronegative atoms, right? Nitrogen, oxygen, or fluorine, then you can have your dipole-dipoles be called hydrogen bonding, which are stronger dipole-dipole interactions. You still have London forces. Ionic compounds. Ionic compounds attract each other and create what's called an ionic attraction or an electrostatic attraction, but they also have London forces. So we always have to recognize that all kinds of compounds are going to have London forces. Nonpolar, polar, polar with a hydrogen on one of the big three, or even just ionic ionic compounds are going to have London forces associated with them. Now, all the combinations or all the interactions, intermolecular interactions that we've been discussing at this point, and if you didn't realize this, you might want to go back and think about this a little deeper. But it's all, so far, all the conversations we've had are all about two molecules that are exactly the same interacting with each other. Well, we know that one molecule or one kind of material, in this case, an ionic compound, can interact with a molecular compound. And we know from a whole chapter's worth of studying that our positively charged ions get surrounded by water molecules, and so do our negatively charged ions get surrounded by water molecules like this, right? And the intermolecular interaction here, I don't know, what do you think? What would we call this intermolecular interaction?
Oh, I think we should call it Fred. I never forget.
Oh, that's a good idea. Yeah, call it Fred. But really, we can call it based on the type of intermolecular forces or type of forces that might contribute to this attraction.
Okay, so water has a dipole.
That's right. Water has a dipole. Now, this isn't between two water molecules, so this isn't a hydrogen bond. It apparently is between the oxygen and a positively charged ion.
Well, I don't know. What would you call it?
Well, you'd call it an ion-dipole interaction.
Oh, okay, all right.
And over here, we would call it the same, ion-dipole interaction. It doesn't need to, you don't need to express that this is a negatively charged or this is a positively charged. A dipole can, and if a dipole exists, it has a positive and a negative charge. So an ion-dipole interaction can be either one of these combinations. So that's an example of ions dissolving in water, ions and molecules coming together. But we also have ways of using these intermolecular interactions to describe what we call solubility. And we'll talk about that next time. All right, good work.